Okay, so this is our third talk in the MRI series, and this is going to be a talk on some of the more common sequences, and I'm going to focus on showing you these line diagrams and how those are written and how things are played out on that. So this is stuff I'm going to cover: spin echo, fast spin echo, inversion recovery, gradient, and echoplanar gradient, including diffusion. And you may say, hell, there's 100 million different whatever sequences. Aren't you going to talk about that one? No, I'm not, because you don't need to know that. Remember, MRI is something that like people do full PhDs in. You could spend 4 or 5 years studying nothing but MRI and still not know everything. The nice thing is that people writing the multiple choice questions don't know everything. They're radiologists too, and this is all you need to know to get the majority of the questions right, I would assume. I can't imagine them going into more obscure sequences, and these are the more common ones. And hopefully I can teach you enough that even if they would show you something that I don't talk about, you could sort of figure it out and get the questions right. So generally speaking, there's two different general categories. There's spin echo, which uses a 180-degree rephasing RF pulse, and then there's gradient echo, which doesn't. So let's talk about the spin echo first. I described this a little bit in the prior talk, and I'm going to review pretty much what I said last time and then build on that. So spin echo is composed of a 90-degree RF pulse followed by a 180-degree rephasing pulse. The rephasing pulse is done at exactly 1/2 the TE, or the time of echo, and the sequence is repeated, and the TR, until K-space is filled. So 4 basic steps here. The first one is your slice selection. So a slice selection gradient is applied the same time as a 90-degree RF pulse, called the selection pulse, is done. Next, a phase encoding and frequency encoding gradients are applied. After that, a 180-degree refocusing RF pulse is given, and before and after this pulse, 2 identical slice selection gradient lobes are applied to help to correct for undesirable spin on the edge of the slice. This is what makes this 180-degree pulse is what makes a spin echo sequence a spin echo sequence. 90, then 180. That's the key point that you need to remember. And if you're looking at these things, that's what you want to see. Small one followed by the big one. The last thing is a second phase encoding gradient that's applied at the same time as the readout echo, and this process is repeated for as many times as you need to get your imaging done. And remember that the time between the 90-degree pulses is your TR, and from about halfway through that 90-degree to the time you get an echo is your time to echo, or your TE. So, mentioning it again, so do you remember why we give this 180-degree pulse? I mentioned it before. Basic idea is that in an ideal world, the magnetic field is homogeneous, but we don't live in an ideal world. The pulse is given to try and improve the heterogeneous nature of the field. And that's the reason that spin echo gives us a T2 instead of a T2 star. And that's a testable point as well. Spin echo, you're looking at a true T2s, or supposedly, or you're trying to anyway. Okay, so building on that, we're going to go on to another kind of spin echo, which is a more modern kind of spin echo, the fast spin echo. Because the line and K-space is filled at each TR with a traditional spin echo, the TR contributes to the duration of the sequence. And because of that, you've got really long TR times. It's the reason that true spin echoes have historical significance. In other words, that thing that we just talked about, that's not done anywhere anymore. It just takes too long. That was like old school. Now there's different types of fast spin echo, and that's what's done more modernly. So it's a little bit different. Looks something like this. So it is a spin echo sequence. So how do you know it's a spin echo sequence? Because we do 90 followed by 180. That defines a spin echo sequence. So when you see that 90 and then 180, you're in the spin echo world. So the idea behind fast spin echo sequence is to reduce the TR, which I already mentioned is a major contributing factor to the duration of the study. And this is done by applying multiple 180-degree refocusing pulses, each of which results in an echo. A couple of things that are worth knowing that are testable is that this fast spin echo has an effect on T2. With each progressive echo train, there's transverse signal gradually decreases, and this is something that's referred to as T2 blurring. Another thing to know is that there's this term called echo train length, or ETL. Basically, that's the number of echoes in the same TR. So remember, your TR is from 90 to 90. So the number of echoes that you get, each one of these echoes that's occurring after the 180 is your echo train length. And the table time is a little bit different than a normal spin echo, which is like your TR times your phase encoding steps times the number of excitations. For a fast spin echo, you think about more of just, your table time is approximately proportional to 1 over the echo train length, so something like that. So because these things are different, anytime there's anything that's different, it's testable. And remember, the idea behind fast spin echo is to reduce the TR, which I already mentioned, and mentioning again, is a major contributor to the duration of the study. All right, so moving on to this idea of inversion recovery. This is a little bit different. So this time, notice that instead of starting with 90, I'm starting with 180. So it's you've got this additional 180 in front of the 90 and then 180. So it's still sort of spin echo in this particular case because you did a 90 then a 180, but it's this special kind of spin echo this right here makes it different. This is what makes it an inversion recovery, and I'll explain that. Basically, instead of starting with 90 degrees, you start with 180 degrees, and they refer to this as a preparation pulse. I'm making quotations in the air. Preparation pulse. So you wait for relaxation of the thing that you want to saturate. That could be water, that could be fat, that could be myocardium, that could be any number of things. And then once it's at its null point, then you deliver a 90-degree pulse. And the time between the 180 and that 90-degree pulse is what's referred to as the TI. And that determines what you're going to be nulling. So TIs are different for different things. Water has a different TI than fat has a different TI, than myocardium has a different TI, than whatever. So that's variable, and that's what makes each one of these things different. So, for example, an example of an inversion recovery sequence is STIR. That's one you're probably familiar with. STIR is an inversion recovery pulse sequence that uses a TI that's sometimes referred to as tau. That's the T. And that corresponds to the time it takes fat to recover from a full inversion, 180 degrees, to the transverse plane. So right there. And at that level, there is no longitudinal magnetization corresponding to fat, which is different than CSF or whatever at that particular time point, and that's referred to as a null point. And it is at that time, like this, that you give your 90-degree excitation pulse. Because there's no longitudinal component of fat at that time, because you hit it with that 180 degree before, and it's recovered right to this point right here. This is a magic point. There's no transverse component for the excitation of that signal from fat, so basically there's no signal. So stir is short. The TI is around 100 to 175 milliseconds, and that value is going to change at different field strengths. It's important to note also, this is highly testable and practical, is that you can't use stir in conjunction with gadolinium. The way that gadolinium works is that it shortens the T1 times. It makes things that have gadolinium in them brighter on T1. That's just a T1 effect, and that's why you give GAD with T1 sequences, not with T2 sequences. So what GAD does locally is it shortens T1 of those tissues that have GAD in it, making them bright. Well, the inversion time of gadolinium is pretty close to the inversion time of fat. So if you did a stir on somebody that had GAD, you would null the fat, but you would also null anything that enhanced. So you never see a contrast enhanced stir. Now we do fat suppression all the time with contrast enhancement, but it's a different type of fat suppression. It's not stir. Now, so that was stirs for nulling fat, but you can also do an inversion recovery for CSF, and that's referred to as flare. And then I mentioned also in the cardiac MR talk that, an inversion recovery can be done for myocardium. You can do an inversion recovery and null pretty much anything. It's just going to have a variable TI time. So here are the take-home points for inversion recovery. You start with 180 degree, so 180, 90, then 180. The TI is the time to inversion, and that's what actually does the dictating for what gets nulled. Stir is short, and flare is long relative to stir, and you can't use stir for gadolinium. Okay, so now we're moving into the category of the second major type. So gradient echoes are not spin echo sequences, they are gradient echo sequences. So this is like red states and blue states, or Coke and Pepsi, or whatever. They're two radically different things. Not that radically different, but they are different. So what makes them different is that gradient echo sequences, one, use a flip angle that's less than 90 degrees, and two, and this is the more important part, they do not have a 180 degree pulse. So when you're looking at the sequence diagrams, notice there's no 180, it just goes 90, 90. The advantage to this is that a low flip angle allows for faster recovery, which gives you shorter TR and TE times and a faster scan. The flip angle is used to determine how much transverse or how much longitudinal magnetization is going to be used. Now, because there's no 180 degree pulse, you're dealing more with a T2 star than a T2. So that's a difference, right, between spin echo and gradient echo. Remember that differences are testable. For the same reason that you don't have this 180 degree pulse and you're dealing with T2 star, which remember is these field inhomogeneities, gradient or GRE sequences are more susceptible to susceptibility artifacts. That's why you see blooming and stuff on gradients, and you don't see it as much on spin echo sequences. So if there's no 180 degree pulse, how do you create an echo? I thought that was part of what created that echo. Instead, gradients use bipolar readout. Basically, frequency encoding gradient is used. So it's something sort of like this. For each one, you're generating a little bit of signal. The take-home point is flip angles less than 90 degrees, no 180 degree pulse. Because there's no 180 degree refocusing pulse, you're more susceptible to susceptibility artifacts. In other words, metal, air, those kinds of things. All right. Lastly, we've got echoplanar imaging, which is um, a sort of a combination. Well, you can do it. So echoplanar can be done with spin echoes, 90 plus 180, or with gradient echoes, 90 plus a bunch of gradients. Echoplanars are very fast. They're one of the fastest acquisition methods. And you can, you can get a lot done. One RF pulse is used to acquire data for an image, sort of like a single shot. The sequence works by turning the phase encoding and frequency encoding gradients on and off very rapidly, and because of this you get a really rapid filling of K-space. Now, compared to a regular gradient, if you're doing an echoplanar that's a gradient, the sequence is even more vulnerable to magnetic susceptibility. And that gives you better tissue contrast and is faster. Now, all this gradient switching on and on, this is the noisy one. So I think in my book, pretty sure that I call echo planar imaging the noisy one. So that's the thing to remember. That's the one that can like damage your ears and stuff like that, is this echo planar. So diffusion imaging is a spin echo. DWI is usually a spin echo sequence where it's a type of echo planar that's done with spin echo, and gradients are applied on either side of a 180-degree pulse to sensitize the sequence to changes in diffusion. So something sort of like this. So this is a demonstration of something. I'll just back up for a second and say that, there's this idea of Brownian motion or whatever, where water molecules are flowing around sort of randomly when they can. They don't just hold still. There's like moving around that happens. So depending on whether or not there's free-flowing stuff or there's or if it's stationary, you can image. Sort of, that's like a thing that you can find out about your tissue. Certain disease processes restrict diffusion. We talked about this throughout all the different clinical talks. Stroke, abscess, bacterial abscess, anyway, certain infections, a whole bunch of different stuff. So, tissue with restricted diffusion is going to be bright, whereas normal free-flowing tissue that's not restricted is going to be dark. So here's why, and here's an example of restricted diffusion. So we've got a stationary molecule here, and we're going to bring in our 90-degree pulse. So this has been energized with this 90-degree pulse, and then we're going to bring in our 180-degree pulse, and that is going to create an echo, and that's going to be, we can acquire signal off of that. So that's restricted diffusion, and therefore it's going to be bright, right? We generated signal, so it's going to be bright, held still for both the 90 and the 180 degree to hit it. Now, here's another situation where you have normal diffusion, where here comes the 90 degree, okay, and it's charged up, ready to go, but it moves because it's moving around normally, and when the 180 degree comes in, it misses it, so there's no signal, and that's why it's dark. So we're talking about changes that are happening really fast, okay? So this is why, you're not seeing moving blood, restrict diffusion, those kinds of things. You are instead seeing, it's sort of at the microscopic level that you're seeing these little changes. But it's the same general idea of this thing that's moving out of the way, causing a void in signal. And that's why you get flow voids. Like this here is an example of a CSF pulsation void, where CSF is at one point in time gets hit with a 90 degree pulse, and then it moves, misses the 180 degree pulse, and then it ends up black. So as you're wandering through here, you can also notice flow void in vessels, right? Vessel flow void, vertebral flow voids, and then you also see this stuff here, which is the CSF pulsation. So moving stuff on spin echo, because you do 90 and 180 degree, will generate a flow void. That's why flow voids happen. Echo planar is super fast, so that's showing you those little tiny flow void kind of thing that's happening more at a microscopic level, and that's your restricted diffusion, or your lack thereof of restricted diffusion. So there's a thing called ADC, apparent diffusion coefficient, and I'm sure you know that ADC is necessary to read diffusion correctly. So an ADC map is calculated by obtaining a set of images without diffusion gradient, which is like the poor man's T2, and a set of images with diffusion gradient. And then you do a logarithm of the ratios. Low signal is true restriction, and high signal is T2 shine through. T2 shine through occurs when lesions or areas have a very long T2 decay time, and they're going to remain bright on the diffusion or the trace image. So it's difficult to know whether they represent an area of restricted diffusion or not, but by producing these ADC maps, that allows you to be able to differentiate between them by correlating with the ADC. So in other words, bright thing here, dark thing here, real, a little bit of bright stuff here, little bit of bright stuff here, not real, T2 shine through. So a take-home point is to think about diffusion as a type of tissue weighting. Just like TE and TR determine how much T2 or T1 or proton density you've got going on, diffusion has this thing called a B factor, and that controls how much tissue's ADC contributes towards the weighting of the image. So if the TE and the TR are long and the B is 0, or your B is 0, then the image is basically a T2. So this looks pretty much like a T2, right? But then as you increase the B factor, you can get a 500 or 1,000, depending on how much this diffusion is actually playing into the creation of the image. So typically, B0 is done and a B1000 is done. You're like, so if you missed the prior point or it didn't sink in, you're like, why am I wasting my time doing these different things? Why not just do the B1000? Because you need the B0 and the B1000 to be able to calculate your ADC map. So that's why these are required, and you have them to look at. All right, so finishing up, let's compare, let's see if we can figure out which one is which. So yellow, orange, red, and blue are all different types of sequences. So let's see if we can figure them out. Let's start up here first. So we've got a 90 degree followed by a 180 degree. So that is a what? That is a spin echo. All right. We know that's a spin echo because that defines a spin echo, right? I pointed out 90 followed by 180, spin echo. Don't need to look anymore. What about this one here? This one's 90, also followed by 180, but then it's a bunch of 180s. So this is a fast spin echo. Still a spin echo if you've got a 180 degree refocusing pulse. So what about this guy here? Instead of going 90 and then 180, he went 180 and then 90. So this is your inversion recovery, right? This time here is your TI. And then lastly, we've got one that doesn't have a 180 degree refocusing pulse. And we said that was gradient, remember? Flip angles less than 90 and no 180 degree refocusing pulse is a gradient. Okay, so that's the end of the sequence talk.